We are going to talk today more about the carbon cycle because really in terms of Earth system science issues, this is our big one. Our big one is the carbon cycle and the potential problems that our use of fossil fuels and land use changes in particular are sort of altering the climate. And then we're also going to talk about human population because really those two are tied together. We are now an enormous population. If we weren't such a big population, we could probably do what we wanted to a certain extent, and we'd never be able to sort of have the effects that we're seeing globally. So what do you think my map here represents? Is it's a little bit different from the normal map you see. What do you think it's showing? Population, absolutely. So you can see Canada more or less disappears completely. India expands massively, so you can really see where a lot of the world's peoples are. And we'll look at the end of today about sort of energy resources, which countries are using the most. And also we're then going to relate this back to population and say, well, how much per person is that? Because obviously those are two very different things actually. And you can probably tell what side of the wall we fall on. Okay. So the course evaluation is live, and I know you have to fill lots of these in every single quarter, so it must get really frustrating. But I do really value your opinions on the class, and I will be teaching this again next year. So please do take this opportunity to let me know what you found helpful, what you didn't find as helpful, and obviously those scores also broadcast now to you as well on the ETA evals. Okay? So it's open until the Sunday before finals week. I don't, this is important because people do this every year, I don't get to see those results until I've submitted your grades, okay? And so if you want to ask me something or tell me something, apart from that you want the final to be easy, I'm not going to necessarily listen to that. But please come speak to me because I don't see those until way after the end of the class. Okay. So this is where we got to on Friday with Alicia. We were talking about the carbon cycle, and the reason that it's so important and the reason we really want to understand this so much more is that we want to know what will happen to the carbon that we're putting back into the system. So the carbon that we're putting back into the system now from fossil fuel use has been locked away as part of the geosphere for sort of tens of millions of years, if not longer. And we're putting it back into the atmosphere. And what we want to know is, how much of a problem is that? Is that carbon going into the atmosphere and then disappearing out again immediately and not going to bother us? Or is it actually going to build up and cause us significant problems? So that's really the underlying sort of point of wanting to understand the carbon cycle. And so with her, you talked about the different reservoirs, the different processes that put carbon into those reservoirs and sort of take carbon out. And then you also thought about sort of the time scale of those changes. And then lastly, we didn't have as much time to talk about these feedback loops. So I wanted to give you a chance, because we haven't talked about feedback loops for a while, but we're coming on to climate next week. And climate is all feedbacks. So I wanted to make sure that you haven't forgotten how to do these. Okay? So you remember this question. And we had a little bit of a slip up on Friday because I think Alicia said that one of them was a negative and she was momentarily confused. So I'm not going to ask the question for a couple of minutes. I want you to think through and draw out, just like we did, those different feedback loops. Okay, see, this is a really useful study exercise. So think about those 4 different feedback loops and see if you can work out. So if you start off by increasing carbon in the atmosphere, if you follow the loop around, does it lead to a further increase? In which case, remember, it's a positive feedback. Or does that initial increase, if you follow your loop around, lead to a decrease again? Okay, so I'm going to give you a couple of minutes to go through these and think about it in more detail and talk to your neighbors because they might have opinions for you as well. Okay? Right, I'll ask the question. So let me know which one you think is a negative or a stabilizing feedback. So has everyone had a chance to make their voice heard? Yes? Okay. Let's take a look and see. Oh, hang on, I've gone back one, haven't I? Sorry about that. Forward, forward. There we go. Okay, so we have a bit of a tie. We have a tie between B and we have a tie between C. Okay, so let's look in more detail at C, because that's the winning one. Okay, so let's take a look. So here's some I prepared earlier. So C was my oceans one, wasn't it? So here you can see on the top, okay, I have the amount of carbon in my atmosphere. If I increase the amount of carbon in my atmosphere, if I increase this, what happens to the temperature of my atmosphere? It increases. What type of arrow is that? Is that a normal one or one with a circle on the end? Normal. If I increase the temperature of my atmosphere, what do I do to the temperature of my oceans? Increase it? It's a fairly obvious one, okay? Here's the problem though, if I increase the temperature of my oceans, how much carbon dioxide can I actually dissolve in them? Less. Do you remember we said on a hot day your soda goes flat, right? As you heat up the ocean, as you heat up water, you can actually dissolve a lot less carbon dioxide in the ocean. So we're going to decrease the amount of CO2 we can dissolve in the ocean. So we're going to have a funny arrow with a circle on the end. And if we're decreasing the amount of CO2 we can dissolve in the ocean, where is more of that CO2 going to end up? In the atmosphere, okay? So we're going to therefore go ahead and increase the amount of CO2 in our atmosphere again, okay? So is this a positive or a negative feedback? It's positive, okay? So I think for most people in the room, that may have caught them out, but that is actually a positive feedback loop. So in reality, the correct answer was this one, because as we increase carbon in the atmosphere, does that make plant growth easier or more difficult? Easier, because they want CO2. It's easier for them to take out that pretty small amount of gas from our atmosphere. So we increase plant growth, okay? If we're increasing the amount of plant growth, we're increasing the amount of carbon going into plants. What do we do to the amount of CO2 in our atmosphere? We decrease it, okay? So in this case, this is our little stabilizing. It's a very small little simple loop. But all of those other ones on there were actually positive feedback loops, okay? So if we go back and take a look at a couple of these other ones, so our people that voted B were a little bit, or they were right in this case, okay? So our first one we've talked about a lot already, the fact that we have lots of carbon in permafrost. If we thaw out that permafrost, it's just like leaving your freezer door open for several days as you go away on holiday. It's going to decay, and that carbon is going to be returned to the atmosphere. So A is definitely a positive feedback. And D, which was a new one for us, but actually we're going to talk a little bit more about it today, is that we have enormous, enormous amounts of this really strange substance called methane hydrates, or methane clathrates. It depends what you're reading at the time. But it's basically just methane gas that's trapped in sort of ice. And so you saw that really amazing photo that Alicia had where you can basically hold a sort of really cold lump of ice and set fire to it. It's really weird stuff, okay? And so again, as we increase our atmospheric temperatures, we're going to increase ocean temperatures, and the concern is that we may start releasing some of this methane from the ocean floor. So that's a little concern. It's not an immediate one though. Okay. So this is sort of a little summary of a lot of those processes that we talked about on Friday that make up our carbon cycle. So you can see that we have our reservoirs there, our things containing carbon marked in black. And then we have little arrows and numbers in blue, which represent those different processes, those fluxes, the sources and the sinks to our different reservoirs. And you can see that one of the reasons why the atmosphere is complicated is because there's a lot of different things that can sort of be a source to the atmosphere, but also a lot of things that can be a sink. So it's not necessarily a simple story that we're just burning carbon and we're putting it up there. It then is actually going to a number of different places, which is actually a very good thing for us. So there's a little summary. I find diagrams like this easier to study from than lists. And this is sort of what Alicia ended with, this amazing, very famous, what we call the Keeling curve. If you ever take any class with me, this pops up, okay? Because it's actually one of the most important graphs that we've sort of produced in terms of time series of measurements over the last sort of 50 or longer now. And this was quite a stubborn guy, and he just decided that he wanted to measure this, and he was very precise. And I think his son now might have taken over. It's a family trade, maybe. I could be making that up, though, so don't take my word for it. And so you can see that we have these wiggles that represent our sort of photosynthesis and respiration, each sort of seasonal cycle almost. But the overall trend is, of course, rising. And the reason that it is rising is because of us, okay? But you'll notice that there are other sources of carbon dioxide that could go into the atmosphere. So we have things like volcanoes, we have things just like plant respiration, animal respiration. And so one of the questions that I used to get asked a lot was, well, how do we know that that extra CO2 that is in the atmosphere is actually from us? And so I wanted to spend a few minutes today talking about something that isn't in your book, so I know that's a horrifying prospect. But I think it's a really interesting sort of story. So how do we know that that carbon dioxide rise is actually due to us? There's a couple of different ways. So first of all, we're taking fossil fuels and we're burning them. So we're putting CO2 into the atmosphere, but what gas might be decreasing if we're burning things? Oxygen. Funnily enough, that's what we see. We can see a corresponding decrease in the amount of oxygen present in our atmosphere. We're not all going to suffocate. It's a tiny, tiny loss, about 1.1% or something. But remember, our atmosphere is consisting of maybe 20% or so oxygen, and so even that change is pretty substantial. So we know that something has to be burning. And then the question is, or respiring, because respiring would also use that oxygen. So then the question is, well, how do we know that that sort of burning process isn't just sort of natural vegetation or isn't just plants respiring? And the answer to that is isotopes, which is everyone's most favorite thing in science. Okay, so remember we talked about isotopes way back in the course now, but isotopes are basically the same element, but they have ever so slightly different weights. So for our carbon, we have 3 isotopes. We have carbon-12, which is by far the majority. Over 99% of it is carbon-12. But we also have a small amount of carbon-13. So it has 1 extra neutron in its nucleus. And then lastly, we have something called carbon-14. And carbon-14 is different from those other 2 because it's actually radioactive. It decays away through time. It's produced really high up in the atmosphere, and then it gets incorporated through the atmosphere, through the surface ocean, into us as part of the biosphere. But say if I sort of died and became a skeleton, if you dug me up in 50,000 years, I wouldn't have any carbon-14 anymore. It would have decayed away, okay? And so what we can do is we can start looking at these different sources of carbon dioxide to our atmosphere and looking at what sort of ratios of that 12, 13, and 14 they have in them. So for example, if we look at trees, life is pretty lazy. I'm pretty lazy. Don't know about you, but if I get the option of lifting up something really, really heavy or something pretty light, I'm going to go with the pretty light one. And that's what life does. It much prefers that carbon-12 because it's really light. It's easier for that sort of to be processed by those plants. So what we see is that in plant material, in any sort of biological stuff that contains carbon, we see a lot more carbon-12 than carbon-13. We only have a little bit of carbon-13. Okay? If we compare that to, say, what's coming out of volcanoes, volcanoes don't care whether it's 12 carbon or 13 carbon. Okay? That's just sort of CO2 that's coming out of the earth. And so actually the carbon in sort of stuff in the CO2 coming out from volcanoes has more carbon-13 in it. Okay? So we're starting to be able to differentiate these. And the other thing that you can see which is different here is that this tree has been living recently. It's been living in the last 50,000 years. Oh, pardon me. 50,000 years or so. And so it's incorporated some of that 14 carbon from the atmosphere, okay? and that hasn't had time to radioactively decay away yet. So we will measure carbon-14 in the carbon from this biosphere, from this life. But we're not going to see any carbon-14 at all in what's coming from volcanoes, right? Because that carbon is coming from deep within the Earth, and so it hasn't been exposed to the atmosphere. So we're not going to have any carbon in there. Okay? Does that make sense so far? Yeah? Everyone looks slightly terrified. So, my question for you is, what do you think the carbon isotopes will be within fossil fuels? Okay? So, I want you to think for a minute about, and sort of chat to your neighbors. Do you think there'll be lots of carbon-13 or a little bit? And do you think there'll be lots of carbon-14 or none at all? Okay? So, talk to your neighbor for a second, and then I'll ask the question. Okay, I'm going to ask the question now. So vote for one of the A, B, C, D. So think about what fossil fuels are made of. Okay, I think that's everyone. So let's take a look. This is my mean question of the day, by the way. It's pretty tough. Okay, so there's a bit of a spread, which is fair enough. So what are fossil fuels made of? Fossils. Okay, they're made of old plant material or old sort of plankton, lots of little tiny microscopic creatures that floated around in the ocean. So do you think they are going to have a low carbon-13 or a high carbon-13? Do you think they're going to be more like my plants or more like my volcano? More like the plants, absolutely, because they're from fossil life. They're from the biosphere, and so when they were growing, they did the same thing. They wanted more carbon-12. They didn't want to take that heavier carbon-13. So just like life today, there's lots of carbon-12 in fossil fuels and not a lot of carbon-13. Okay? How old are fossil fuels? Thousands of years or millions of years? Millions of years, absolutely. It takes a really long time to make our fossil fuels. And so is there going to be 14 carbon in my fossil fuels? No, because it's going to have decayed away. So even if it had carbon-14 to begin with, which it probably did, it won't have any left at the end. So which is my correct answer on here? It's C. Okay, so that's my really difficult question of the day. But I think it's really interesting how we can use these different isotopes to look at these things. So if you're struggling with this, think about it a little bit more carefully. Okay. And so if we look at the atmosphere, if we're putting lots of fossil fuels in there, we're going to expect to see lower amounts of carbon-13, which is what we see. You can see this is our isotope ratio through time. Don't worry about the notation, but what that's basically telling you is that we're putting lots and lots more carbon-12 into our atmosphere and less carbon-13. Okay? And then lastly, if we look at the amount of 14 carbon we have, the atmosphere was also starting to get less and less carbon-14 in it, okay? But you can see that my graph ends at 1950, okay? Because we really screwed up the amount of carbon-14 in our atmosphere by nuclear bomb testing. When you explode nuclear bombs, you also make lots of carbon-14, and so it's really messed up our nice atmospheric signal of a decreasing carbon-14. But before 1950 even, we could see that that was happening from us burning, okay? So that combination of the oxygen in our atmosphere decreasing shows it has to be burning or respiration. And we can see from the amount of radiocarbon decreasing in our atmosphere that it has to be really old. It can't be something that lived recently. It has to be something much older. And so really that only leaves us with the fossil fuel burning. Okay? So anyway, a quick aside, but carbon isotopes are really helpful because they help us quantify some of these fluxes. They help us tease apart which of these sources and sinks is important for the atmosphere. So they're really very, very important. So If we said that we've put lots of CO2 into the atmosphere, first of all by deforesting large areas, and then by burning lots of fossil fuels, the question is, where has that carbon gone? Because only about half of the carbon that we've put into the atmosphere is still there. The rest of it has gone, and you can see from this diagram where it's going. So this is sort of the amount of carbon dioxide, or the amount of carbon that has gone into the atmosphere between 2003 and 2012. So each year, 8.6 gigatons, so billion tons of carbon, was released into the atmosphere by using fossil fuels, and also cement produces a lot of CO2. But we can see that the atmosphere only grew by 4.3 gigatons per year. So in reality, we actually lost sort of another chunk of that to the oceans by dissolving that carbon dioxide in the oceans. And we also lost a remaining part of that to the land. So yes, we're deforesting large areas and burning and everything else. But actually right now, the land is taking up quite a lot of that carbon that otherwise would be in the atmosphere. So here's our little map of the oceans, and the colors here just show that where the carbon is going into the ocean is in those cold regions where it's more easy to dissolve it. But also, especially in the North Atlantic, what's happening is that, remember, that's where we have deep water forming. So that water is getting nice and full of CO2, and then it's sinking right down to the base of the North Atlantic. So we're locking away a lot of carbon in the waters up there. And then the rest of it is going into the biosphere. So that seems a strange idea to us, because we're constantly told how we're deforesting. But actually, we've seen quite a lot of regrowth in some forests, especially over on the East Coast now. You can find all of these weird little hidden away lost villages over on the East Coast. And we also are seeing thickening of forests, because especially in California, until pretty recently, the policy has been to suppress fires. It's one of the reasons that forest fires now are so intense and so damaging, because we haven't allowed these frequent fires to clear out the undergrowth. And so when they do catch fire, then they tend to be much, much stronger and more intense and more damaging. And so that's sort of also increased the amount of carbon locked away in the biosphere here. Okay? So that's where it's gone so far, but the question is, can we rely on those to continue taking up quite as much carbon as they have been doing? And the answer is a big emphatic no. And it's a big emphatic no because, first of all, we're warming our oceans, and as that happens, we're going to sort of limit the amount of CO2 we can dissolve. And also, there just is a limit to how much carbon dioxide we can dissolve in our oceans. And secondly, we've already talked about this fact that the biosphere is limited by things other than carbon dioxide. So we can't grow forests over the Mojave Desert. It's too dry. We can't grow forests elsewhere. There's a limit to how much extra biosphere we can create, especially if we're then using that land for agriculture. So we need to think about this. These processes have been helping us out, but that's not necessarily going to continue. So, just to drive the point home and make it really cheerful, how long do you think it will take for the carbon dioxide that you produced by driving your car around this weekend, how long will it take to stop affecting our climate system? So remember, our climate system incorporates things like our surface and deep ocean, our biosphere, our atmosphere. So how long will it take to sort of leave our climate system? I think that's everybody. So the 45% were right. Hundreds of thousands of years. Okay, because remember, our climate system is sort of involves the ocean, the land, the biosphere, everything else. So even if it goes into the biosphere, into the ocean, it's still circulating in our climate system. It can still sort of come out again. If we want to really lock away that carbon, we have to do it in the form of sediments or in the form of fossil fuels. And those take a really, really long time to form. Okay? And so really what we're thinking of is that extra pulse of CO2 that we've put into the atmosphere, even if we stop tomorrow, It would take hundreds of thousands of years for that carbon to gradually get locked away in sediments to get back to where we were before. And that's something we can see in the past. If we've seen enormous volcanic activity or something like that in the past, we can see it, we can time it, we can see that it takes hundreds of thousands of years to happen. Okay? So, worth thinking about. So, let's think about the other cheerful thing today, which is human population. So, we already mentioned this a little bit when we talked about population growth, but we're a very good example of exponential population growth. So our population went a bit crazy sort of earlier in the century, and in 1950, so maybe when your parents were alive, maybe when your grandparents were alive, I'm losing track, but there are only 2.5 billion people on the planet. It's a really cool clock I'll post to the Facebook group, but you can work out from putting your birthday in what number human you were. And I think I was like 4 billionth or 4.5 billionth or something. Today, we have 7 billion people, and that's just within my lifetime, and I'm not that old, okay? And so you can see that in the future, we're going to expect further population growth. And really, the interesting question is how much population growth? Because we are starting to see a leveling off. We're not really exponential anymore. We are starting to slow a little bit. And so the question is will it level off? Will it start decreasing, actually? It's a really interesting question. And related to that question is basically what the carrying capacity of Earth is. Is there a limit on our population growth? If so, what is it? Okay? And really the key point I want to make is that this is an astounding change. We have had an astounding change in our population, and therefore our impact on the Earth in just the last 100 years. And really the fundamental underlying point behind all of our big major environmental issues is really this enormous population growth. We can't continue in the same way that we did before. There's just too many of us. We have to think of a different way of doing things. So this is sort of a little schematic of the phases that different countries go through at different points. Usually in phase 1, what we have is we have a really high death rate, and then we have a really high birth rate, perhaps because we have a really high death rate. And so our total population is pretty low, and it sort of fluctuates around. But at a certain point, we get better sort of medical expertise or medical supplies. We have more resources available, perhaps there's an agricultural revolution, something like that. And so what we see is that our death rates dramatically fall. But we're humans, we still like doing things the way we did before, so our population starts increasing because our birth rate remains high for a certain amount of time. So that's phase 2, when we see this dramatic drop in our death rate, but our birth rate stays high, so we see very dramatic population growth. In phase 3, for a number of reasons you could think of, so women is empowerment, education, just sort of societal factors, you can see that our birth rate starts to drop to match that death rate again, okay? So our population growth slows, and then lastly, we have our death rate and our birth rate are both pretty low, and our population sort of stabilizes again. So which of these phases do you think the USA is in? Compared to other countries around the world, which do you think the USA is in? I think that's more or less everybody. So most people think C. I would argue with that. I think we're more in the D phase right now. I think that's more where we are. Our birth rates compared to worldwide are pretty low. I think it's one of those things where we see a lot of migration, and migration isn't perhaps counted in this, but I would say perhaps we're more phase D. Okay. And you can imagine that other countries around the world, especially perhaps say India, you're seeing very, very rapid population growth in there. So that's maybe more phase sort of 2 or 3. So different countries around the world are at different phases of this. And the question is that, are we going to end up in phase 4 for everyone? There may even be a phase 5 where our population actually starts decreasing again. In some of the European countries now, the birth rate is so low that without migration, their population would actually be declining, which is really interesting, I think. Okay, so let's think about what those limiting factors on our big global population are. So first of all, and I've stressed this to death really, is drinking water. So fresh water supply. And this is sort of the focus of the last Call at the Oasis documentary. And reminder that that assignment is due by the end of Wednesday if you're wanting to do that. So remember, just 3% of our global water supply, or our global water, is actually fresh water. And the vast majority of that 3% is actually locked away as Antarctica or as Greenland are amazing kilometer-thick ice sheets. And what that leaves us with is not very much, actually. Okay? It leaves us with groundwater and those streams and lakes, so maybe 30% of that 3%. And even then, that supply doesn't match the demand. The supply is often sort of much greater at high latitudes where there aren't so many people, whereas you can look at LA, where we have an enormous population and very little water. So our supply doesn't equal our demand. And I think these are some really interesting numbers. Today, 54% of that available fresh water is used. 54% of what is available to us is currently being used by us, mostly for irrigation. If you ever drive through the Central Valley, you can see that. A lot of our water in California goes to irrigation. And the problem is that, as we've mentioned, that's not sustainable. So in the USA, in India, in China, we're seeing a drop in our water tables. I mean, sooner or later, people are going to realize this, and it's going to be unsustainable to continue pumping that groundwater out. So we're going to see shortages there. By 2025, people are anticipating that we might use up to 70% of that available fresh water. We're going to be diverting more of it for human use, especially as our population grows. But remember that we can talk about sort of global again, but remember it's that supply versus demand. And our problem is that a lot of our population growth in the next few decades isn't going to be in areas where there is lots of supply. It's going to be in places which are already sort of experiencing pretty dramatic water shortages. So we're going to exacerbate our problem. We're going to make our problem worse rather than better. Then we have our food supply. So food supply isn't something that we think of very often. But if we think about it, there is a limit to how much food we could possibly produce on Earth. Okay? And so the limits sort of are, first of all, how much available agricultural land is there? And secondly, how much food can we get per little unit area of that agricultural land? And so if we look at, first of all, the amount of agricultural land, today maybe 20% of the suitable land is used. But our problem is that, again, we're not using that sustainably. We're seeing enormous amounts of soil erosion due to sort of our farming practices, and also things like desertification due to either climate changes, but also, again, sort of overgrazing or farming practices, means that actually that number is decreasing. The amount of available land is actually decreasing right now. And soil erosion is one of our big unspoken sort of limits here. And then the last thing is that, have you heard of the Green Revolution? No? Okay. And this is the idea that if you went back to, say, the 1940s, then we were producing a lot less food per area of land. We had amazing technological advances in things like pesticides or fertilizers or different sort of crops that really allowed us to massively expand the amount of food that we could produce per unit area. But the problem is that enormous increase that we've been seeing is sort of leveling off. And we don't really see any massively new, exciting technological advances in our future that will really help us sort of sustain that increase. So we've seen our green revolution, it's sort of leveling off at this point. And so we have a number of threats to our food supply. So things like climate change is going to change where we can grow certain crops potentially. Remember, it's going to really affect our rainfall and precipitation patterns in a lot of areas. Things like disease and biodiversity. Increasingly, the crops that we're growing are, if not genetically modified, but they're certain sort of genetic codes of crops, and they tend to be sort of clones of each other. And what that means is that they're much more susceptible to disease. If a disease comes in to, say, our banana crops, which are all basically clones, then we could wipe out our banana crops pretty easily, because there's not enough genetic diversity to perhaps sort of fight and combat that disease. And so also population growth, just more of us to share that out. So there's a really fascinating guy that came and gave a talk at our department last year, and he runs this sort of Food Security Institute in Stanford, and there's a number of really interesting talks by that group. So I wanted to post that there, and you can learn a lot more about that, and about things like the price of food in different places, and the, sort of the ratios and the types of food that we're going to produce as well. It's fascinating stuff. And this is sort of what it comes down to. So at the top, remember I said that we as humans actually take in an enormous amount of the net primary productivity that is produced each year on Earth. Okay? And so the darker colors there represent our sort of appropriation, our use of more and more of that net primary productivity. And the top diagram is just basically an assessment of the amount. It's just basically a weight. I think what's more interesting is this bottom diagram here, where as you get into the bright sort of pinks and oranges and yellows, then that's actually representing sort of percentages of the available net primary productivity. So in a lot of areas, so you can see along our coast, along the east coast, especially around India, China, and parts of the Middle East, then we're actually using close to sort of 200% potentially of the available primary productivity. Now that's not physically possible. We can't use 200% of something. What's actually happening is that those areas are reliant on imports of food. Okay? There isn't enough primary productivity in those locations to support their population. They need to import food. And that's what we do in our region as well. Okay? But that's expensive. And it sort of relies on good relationships with other countries around there. And as their populations grow, that will become difficult. And then lastly is energy use. And energy use, I don't think is as big a deal. There's a lot of energy out there, and it's not necessarily that we're not technologically able to do it. It's probably just expensive. So energy use, I don't think, is one of our potentially sort of big sources, but it is the source of some of our very big problems. So here you can see the difference between the amount of energy, or sort of the percentage distribution of energy generated in 1973 and 2010, and you can see that there really hasn't been a lot of change. And that's really the pattern that we've been seeing. A lot of our energy, probably over 75% of it, comes from fossil fuels. It comes from oil, it comes from gas. It comes from coal. And that's not really changed, and it probably isn't looking like it will change much more. Things like biofuels and waste, so people burning sort of trees or other stuff. Nuclear has expanded a little bit on 1973, but there's been a bit of a backlash against that recently as a result of the Fukushima plant. So you can see that we have a lot of different sources, but the renewable part of that, the bit that we like to think of, things like solar, things like wind, are really within sort of 1% of the total energy we produce on Earth. And what we'd really like is to bump that up a whole lot. Because, let's have a look at energy use per country now. So, you can see that our big energy users in terms of the world are the USA, Russia, China, India, Canada. Those are some big users of energy. But that's per country. What do you think will happen if we break it down per person? Okay, so that's probably something that doesn't surprise anyone. So Europe, North America, Canada, Australia become much more guilty. We use much more energy per person than say, so even if China is actually producing much more CO2 now than the US, per person, It's maybe half to a tenth, perhaps, of what we're actually using here in the US. And in terms of a lot of our manufacturing is happening in these other countries rather than here. So we are really sort of the end users of a lot of the materials produced elsewhere. So when we take into account per person, we don't look so good, unfortunately. And this is a more fun way of doing that, okay? Has anyone seen this before? Yeah? It's a really cool diagram, I think, and I put it in your notes so you can explore it over your nice long holiday weekend. So you can see that on the left-hand side, again, we have the per country. So you can see United States down here at the heel, Canada up there, China up there towards the toes. And then on the right-hand side, you can see it split down again per person. Okay, and now the big one is Gibraltar, which is this tiny, like 5 kilometer by 5 kilometer area that does a lot of shipping. So I think that's why it's big. So you can start to see these differences, and I think it's really fascinating. So people say to me all the time, well, it's okay, we're going to run out of this stuff really soon. Well, maybe. The idea is that we actually probably have quite a bit of oil left. Not hundreds of years worth, but we have a lot left. And we've really sort of taken in a lot of the accessible stuff. That's our problem. It's getting much more expensive and much more difficult to produce that oil, but we still have quite a bit left. So in my graph here from 2006, in purple you can see how much oil we've already used, and also gas, coal, etc. In pale blue you can see what we know we have left. Those are proven reserves. We know it's down there, we just need to take it out of the ground. And then in yellow is what we think is actually out there, and that's probably a little bit of an underestimate. Okay. So you can see that for oil, we're probably maybe halfway. For gas, we're not even halfway. For coal, we're nowhere close to potentially using the amount that is out there. And then in this other column, we have things like the tar sands, which in 2006 weren't really being exploited, but Canada definitely now is trying to extract the fossil fuels from their tar sands. We've got shale oil, which is now also being exploited more perhaps like by fracking, if you've heard of that. And then we have our methane hydrates, which was a concern because they were down there. We thought we might be able to release methane by melting those. But actually, the Japanese are very clever, and they have found a way of extracting methane hydrates now, which means that that could become a new sort of fuel source, and it could be sort of another source of fossil fuels to keep us going. But there's a problem with that. And the problem is how much CO2 could we potentially put into our atmosphere if we burned all the available oil, gas, and coal, okay? So on this side, we have gigatons of carbon, but on this side, we have parts per million of carbon dioxide, and so think about it in parts per million, because that's what we're most familiar with. So if we ignore shale oil, tar sands, and methane hydrates, what amount of CO2 could we put into our atmosphere just by burning this other stuff? Any final answers? See how good everyone is at adding today. Reasonably good. We haven't done that well today, have we? But I would agree with C. Looks like we have about 200 parts per million of oil. We have about 100 parts per million of gas. And we have maybe 600 of coal. Okay, and all of those add up to 900. Does that sound like a good idea to put into our atmosphere? Does anyone know what the CO2 level was during the last ice age? 200. Does anyone know what it was before we started affecting the atmosphere? 280. Does anyone know what it is today? About 400. So we are having a very dramatic effect on the amount of CO2. Does anyone know what sort of, if we hit over 1,000, does anyone know how long it's been probably since we last saw CO2 levels of about 1,000? tens of millions of years. It was really very different. Sea level then was maybe 70 feet higher. So we're talking about really, really substantial change. So when people say to me, oh, it's okay, we're going to run out. Well, yes, maybe, but not soon enough. And certainly if we're going to stop really catastrophic change, it needs to be a real decision. We can't just run out and by default switch to these other things. It really needs to be a decision. So there are a number of other options. This is the thing. And in most of these cases, the real challenge isn't sort of whether we can do it. We can do it. It's sort of how we can engineer those sort of sources into our supply and make them reliable enough, how we can make energy use more efficient. So it's expense rather than anything else. So things like nuclear, solar, hydrothermal, wind, geothermal, there's a whole variety of other things we could potentially use. And so my questions are, well, I started off by saying, well, what is the carrying capacity of the Earth? How many people could we possibly support? I think the better questions to ask are, how many at what level of well-being? How many with what distribution of that well-being? Are we happy to survive here when other areas are really sort of much worse off? How many with what technology? How many with what sort of environmental conditions? Okay? And how many for how long? I think those are the really important questions to ask. Okay, so that's all for today. On Wednesday, we're going to talk about ozone.